Hey everyone, and welcome back to the Science in 10 virtual field trip series. In our first virtual field trip, we visited some of the oldest rocks in the Pacific Northwest. Rocks that record the breakup of the ancient supercontinent of Rodinia and the development of a passive margin along the edge of Laurentia, the continental landmass that would eventually become North America. Next up, we're moving forward in time a couple 100 million years, from the early Paleozoic to the mid-Mesozoic, as the tectonic setting of the future Pacific Northwest was about to change in a very big way. Before we get started, let's take a minute to quickly recap where we are in the development of the Pacific Northwest. Our story began over 1 billion years ago on the ancient supercontinent of Rodinia, where sediments that would eventually become the Belt Supergroup were deposited. We'll add a little star next to these maps to show the approximate location that would become the Pacific Northwest. Around 750 million years ago, Rodinia began to rift apart, leaving behind a developing passive margin at the edge of the continental landmass of Laurentia, what would eventually become North America. This passive margin slowly accumulated shallow to deep marine sediments, some of which today are present in the Okanogan Highlands as the Meadowline Formation and the Leadbetter Slate. Our region was pretty quiet tectonically for a couple 100 million years, but not the rest of the planet. After the rifting of Rodinia, the continental masses reconfigure themselves into the smaller supercontinents of Laurasia and Gondwana, and eventually into the supercontinent of Pangaea. And just about this entire time, the margin of Laurentia was passive. However, around 200 million years ago, Pangaea began to break up, initiating a major subduction zone where the Laurentian passive margin used to be. Here, the oceanic plate began subducting underneath proto-North America, and along with subduction, marine rocks were transported back towards the continent. And since these marine rocks were too light to subduct, they were added back, or accreted, to the Laurentian continental mass. Along with the accretion of marine rocks came the addition of exotic terranes to the growing North America, and eventually the formation of the bulk of the Pacific Northwest. For our purposes, we've lumped the accretion of literally dozens of exotic terranes into 3 larger groups, based largely on the timing of accretion. That's the important part here. We're not defining the terranes on when the rocks themselves formed, rather when the rocks were added to North America. This field trip is the story of approximately 150 million years of accretion, divided into 3 main phases. First, terranes accreted during the Jurassic, roughly from 200 to about 170 million years ago. Second, terranes accreted largely during the Cretaceous, between 150 and 100 million years ago. And third, the most recent terranes accreted in the Cenozoic around 50 million years ago. To begin, let's head back to where we were on the last field trip, the Okanogan Highlands of northeast Washington. So why start in the Okanogan again? Simple. This is where we can observe some of the first rocks to be accreted to Laurentia, juxtaposed against the rocks of the passive margin. Here's the present-day geography of the Pacific Northwest, with the edge of the Laurentian continent and where the passive margin rocks are found in the Pacific Northwest. As accretion began, rocks and terranes were successively added to the Laurentian landmass, progressively growing the continent outward towards present-day west. The first major group of terranes, also called a superterrane, to be added was the intermontane superterrane, and this accretion took place during the Jurassic. First up, let's check out a smaller part of the superterrane, along Highway 97 in the Okanogan Highlands. From the highway here, looking west, we can see cliffs that are composed of carbonates and other marine-derived rocks. These rocks are part of the Quesnellia terrane, Permian and Triassic marine sedimentary rocks and volcanics that were accreted to Laurentia during the early Jurassic. If we take a closer look at these cliffs, we can notice that the rocks have been quite deformed, dipping, and in some places quite folded. This is exactly what we would expect to happen when a terrane is added to a continent. All the rocks would be subject to some pretty intense compressional stress during accretion. For a look at some of the other parts of the Quesnellia terrane, let's quickly jump over to Kettle Falls on the opposite side of the Okanogan Highlands. This is another pretty great road cut, and unlike the last stop, we can safely get up close to the rocks. No trespassing involved here. The rocks here are a little different than the last location along Highway 97. Here we have a mixture of semi-metamorphosed carbonates and volcanic rocks. And just because for any outcrop there are as many interpretations of the history as there are geologists observing the outcrop, I'll give my interpretation with a grain of salt here. I'm going to interpret this particular outcrop as part of a larger melange of Quesnellia terrane material, where once geologically organized carbonates, other marine sediments, and volcanics got caught up in a literal tectonic blender of accretion. Individual blocks of marble and metavolcanic rocks are present here, even with some secondary pyrite in some of the volcanic rocks. Of course, it's not just material on top of an oceanic plate that gets scraped off and added to a continent during the accretion process. There's other stuff too, which we'll examine at our next stop. For our next stop, we're staying within the larger grouping of terranes that accreted during the Jurassic, but jumping south to the Blue Mountains of Oregon. We've moved quite a bit geographically, and simultaneously a lot and very little geologically. We're at a road cut along US Highway 395, just south of the town of John Day, Oregon, right in the middle of the Blue Mountains province. Conveniently, we also have another geology field class joining us at this stop. Although these rocks here at this outcrop are quite a bit different than what we looked at in the Quesnellia terrane, their story of accretion is very similar. To get at that story, let's first observe the color of these rocks. And again, like we saw on our last field trip, they're green. Quick recap. One way to produce green rocks is through the metamorphism of mafic igneous rocks. In this particular case, the mafic igneous rocks that were metamorphosed were pieces of oceanic crust that got caught up in an accretionary event. This is an outcrop of serpentinite, part of the Baker terrane, which are Triassic and Jurassic igneous and sedimentary rocks of a subduction complex that was added to the growing North America sometime around 180 to 150 million years ago, give or take. As with many outcrops of serpentinite, these rocks began their life as basalts or gabbros at a mid-ocean ridge and were then transported via ridge push and slab pull towards a subduction zone. This particular outcrop of serpentinite is heavily deformed, giving us clues to its torturous past being caught up with accretion. To examine that in detail, let's take a closer look. These small parallel lines on this outcrop are called slicken fibers, features that form from motion on thousands upon millions of tiny faults within this block of serpentinite. These slicken fibers are pervasive throughout this entire outcrop, indicating that in the past, this whole blob of serpentinite was subject to some pretty intense forces and deformation. So here we've taken a look at some of the rocks that are at the bottom of an accretionary complex. Now, let's quickly drive up the road a little bit to see rocks that were a little higher up. Here, we're still along Highway 395, but we're obviously getting into some very different rocks. We're no longer far deep within an accretionary complex, but rather much farther up to where we're seeing rocks that were deposited on the ocean floor instead of metamorphosed ocean floor. These rocks are highly deformed sandstones and shales of the IZ terrane, Triassic and Jurassic sediments that were accreted to North America in the same major group as the Baker terrane. Some of the thicker beds are sandstones, and many of the thinner laminations are shales mixed with turbidites, underwater debris flows that generally slough material off of a continental shelf into the deeper ocean basins. So far, up through now on this field trip, we've seen deep ocean limestones, metavolcanic rocks, pieces of metamorphosed ocean crust, and heavily deformed turbidites and sandstones. All these rocks are pieces of or formed on top of an old oceanic plate and were accreted to North America during the Jurassic. We've also pretty much stayed on the eastern side of the Pacific Northwest. Though for our next stop, we're going to go visit rocks in the far southwest portion of Oregon, but still in the same general group of accreted terranes. Let's traverse almost the entire state of Oregon, from the central Blue Mountains to deep in the Klamath province to the small town of Cave Junction near the California border. Just a quick rest stop here at the Illinois River Valley Visitor Center before we head up a super windy road to the Oregon Caves National Monument. Yes, caves! These particular caves tell a really cool story that fits right in with this part of the Pacific Northwest's geologic history. Not including lava tubes, most caves, including the Oregon caves here, form through the chemical weathering process of dissolution, where weak acids slowly dissolve away soluble rock. The most common type of soluble rock that caves form in are carbonates, such as limestone and marble. And these carbonates initially form in marine environments. But wait, the Oregon caves are at over 1,200 meters elevation in the Klamath Mountains. How do we get carbonates all the way up here? You probably guessed it, accretion. The carbonate rocks that the Oregon caves formed in are part of the larger Rattlesnake Creek terrane, a grouping of rocks that definitely fits the definition of a melange. Of course, everything in the Rattlesnake Creek terrane is pretty blended up now, but it was likely an island arc in the past as it contains volcanic rocks, mafic to intermediate intrusive rocks, serpentinite, and a whole bunch of sedimentary rocks generally associated with deposition or formation in a marine setting surrounding these volcanic islands. This arc accreted at some point during the middle to late Jurassic, and erosion since then has exposed the carbonates and formed these caves. So, enough talk about the caves. Let's make a quick stop at the visitor center and then go on a quick tour. The entrance to the caves here is kind of unassuming, but inside are close to 5 kilometers of cave passages. So let's head in for a couple highlights. Got my headlamp on. A fun thing to remember while we're in the cave is that the entire thing began as pretty much solid rock, and over time, mildly acidic water seeped in along fractures and slowly dissolved away the caverns that we're able to walk through. These caves also have great examples of various speleothems, rock formations that are produced by the precipitation of calcite from water in a cave. We have stalactites, which form on the ceiling of caves, stalagmites, which form on the floor, and columns. What forms in a stalactite and a stalagmite grow together. There are also a bunch of these banana bunch clusters. These form when calcite precipitates from water flowing over the cave walls. Once out of the cave, it's a short hike back to the visitor center, but not without first enjoying the view towards the west, and our next field stop in the western Klamath Belt terranes. For our next stop, we're actually going to head just south of the Oregon border into California. Just because the states change doesn't mean the rocks do. In fact, there are some excellent outcrops of accreted rocks of the western Klamath Belt along the Smith River. First, a quick look at some of the western Klamath Belt rocks along the road. And very similar to other rocks that we've looked at so far, they're green. Once again, we're seeing metamorphosed mafic to ultramafic igneous rocks, indicating that the accreted rocks once belonged to an island arc and oceanic crust, and were added to North America during the late Jurassic around 150 million years ago. The remnants of oceanic crust here are part of the Josephine ophiolite. For a better look, let's hop off the road and down to some of the outcrops that are actually right along the Smith River. We're going to visit an almost full ophiolite sequence later on in this field trip, so here we'll just point out a couple major features. The rocks here started out as sheeted dikes, parallel vertical intrusions of a mafic melt at a mid-ocean ridge that solidified before the melt could fully work its way out to the ocean floor. During accretion, these dikes were altered to greenstone, but some of the remnant structure is still present in this outcrop. If we head upstream and upsection a little bit, we get to a location where we find thinly laminated slates, fine-grained sediments that were deposited on top of the oceanic crust and then metamorphosed along with accretion. These slates are likely the top of the Josephine ophiolite sequence. The accretion of the Josephine ophiolite and the western Klamath Belt, which were in here, have a pretty cool story, and that's a little more complex than just an island arc being added to North America. The Josephine ophiolite likely started out as a back arc basin, spreading and production of oceanic crust that happens inboard of a volcanic arc. As subduction continues, if the new back arc basin crust is weak enough, it will be squeezed between the existing continent and the accreting arc. This will incorporate the oceanic crust into the accretionary complex and sandwich it within the metamorphosed rocks that were the marine sediments and the original arc rocks themselves. Next up, let's take a quick trip north to the Illinois River, staying within the western Klamath Belt, but instead of ophiolitic rocks, we'll visit some metamorphosed arc volcanic rocks. Yes, once again, green rocks. Sorry it's a little hazy out here. We're visiting this area very shortly after some intense wildfires burned through. Here we're along the banks of the Illinois River, one of the few that cuts through the western Klamath Belt. And of course, here we find more metamorphosed basalt. Greenstone, but with remnant pillows preserved in the rocks. These loamy, lumpy shapes to this outcrop are pillows, structures that form when basalt is erupted underwater, either at a mid-ocean ridge or in an island arc style setting. As the basaltic melt hits the ocean water, the outside of the flow hardens and crystallizes almost instantaneously, but the inside remains molten. As the eruption continues, the melt will flow off into various lobes. When these lobes pile on top of each other and fully crystallize, they leave behind what looks like a stack of pillows. But I can't recommend taking a nap on these. Again, these pillows have been metamorphosed to greenstone during accretion. Later on in this field trip, we'll take a look at some pillow basalts that are a lot younger and definitely a lot less metamorphosed. But first, we're about done in the Klamaths and finishing up with the major accretionary events that took place during the Jurassic period. Next stop, as you might guess, more accretion, but a bit younger. From the Klamath Mountains in southern Oregon, we're headed all the way north along the Interstate 5 corridor to Fidalgo Island in Anacortes, Washington. Fidalgo Island is one of over 150 individual islands that make up the San Juan archipelago, an incredibly beautiful place with a really cool geologic story. As you might guess, the geologic history of this area has to do with accretion. There are many similar rock types present in the San Juan Islands as we've looked at so far on this field trip, but the big difference is the timing of accretion. The San Juan Islands accreted a little bit later than everything else we've studied so far. Their accretionary event was during the Cretaceous, around 140 to 100 million years ago, with the much larger insular superterrane, which stretches all the way up the coast through British Columbia. So, while we can say that each individual island in the San Juans has an interesting geologic story, we're going to focus on Fidalgo Island, and we're going to start in the mantle. Wait, the mantle as in the compositional layer that's under the crust mantle? Yep, that mantle. Well, the upper parts of it anyway. For this, we'll begin at Washington Park, just west of Anacortes. This brownish, orangish looking rock, this is peridotite, an ultramafic intrusive igneous rock, which is indeed a piece of the uppermost mantle. Fresh, this rock is dark green to black and full of olivine and pyroxene. Heavily weathered though, like this outcrop, the iron-rich minerals can rust and much of the olivine has been altered to serpentine through various types of metamorphism. So why is this particular peridotite important? Well, it's not only Field Dog's favorite outcrop, but it's also the base of a world-class ophiolite sequence here on Fidalgo Island. As we mentioned earlier, the rocks of the San Juan Islands are part of a larger group that accreted during the Cretaceous, and part of that accretion included this ophiolite. The Fidalgo ophiolite contains rocks from the full section of the oceanic crust, from its base at the uppermost mantle here to clastic rocks that were deposited on top of the crystalline oceanic crust. If we let Field Dog wander around for a little bit, we can take a closer look at this weathered peridotite. Again, this ultramafic rock is mostly pyroxene and altered olivine. Some of the shiny bits we can make out in this outcrop are individual cleavage planes in the pyroxene crystals, but otherwise, since this rock is so weathered, it's pretty grungy. So from here in the peridotite, we're going to work our way up through the ophiolite sequence. The next stop is a location a short hop away on Marine Drive. Finally, an outcrop that isn't green. But don't worry, we'll be back into some green rocks soon enough. The rocks here are gabbro, the intrusive version of basalt that crystallized at the base of the oceanic crust as it was being formed. Taking a close-up look, we can see immediately that the rock here is far less green than the ultramafic peridotite, since the gabbro has a much higher percentage of plagioclase feldspar. In this outcrop, pyroxene and minor olivine are the dark crystals, and the plagioclase feldspar are the lighter and colored portions in here. Moving upwards through the Fidalgo ophiolite rocks, we are also headed to the highest point on Fidalgo Island, Mount Erie. The rocks along the summit, and most of the bulk of Mount Erie, are plagiogranites, intrusive rocks composed primarily of plagioclase feldspar, quartz, and minor mafic minerals. So how would these rocks form in the oceanic crust? Well, let's think back to Bowen's reaction series and run it as we are cooling and crystallizing an ultramafic to mafic melt. Basically, when the oceanic crust is created, it starts from a mafic to ultramafic mantle-derived melt. The first parts to crystallize are the mafic minerals such as olivine, pyroxene, and calcium-rich plagioclase feldspar. These will often form the gabbros found at the base of the oceanic crust. But what about the leftover melt? Some pyroxenes and amphibole are left in the melt, along with a lot of plagioclase feldspar and remaining silica. This leftover melt can intrude into a gabbro or remain at the top of a magma chamber as a heavier gabbro solids sink to the bottom. When this melt crystallizes, we're left with a plagiogranite. It also happens to be fairly resistant to erosion, which is why Mount Erie is such a great viewpoint. Can't stay up here for long though. There's still the rest of the ophiolite to work through. Continuing up section, we enter the extrusive parts of the ophiolite. Originally sheeted dikes and pillow basalts, these have been slightly metamorphosed, so the outcrop that we see here along Highway 20 is good old greenstone. Now here, we're pretty much at the top of the crystalline or igneous parts of the ophiolite. So our final location on Fidalgo Island will be the sediments that were deposited on the ocean floor. For this, we're taking a short trip over to Deception Pass. The cliffs here along this always busy highway are a particular type of sandstone, greywacke. Greywackies are pretty unique in that a higher percentage of the grains are made of feldspars, indicating that the sands did not travel very far from their initial source. If we sneak in between these parked cars here, we can get a better look at the rocks. Greywackies are generally associated with turbidites, underwater sand and water avalanches that occur along continental shelves or around volcanic islands. These turbidites can transport and deposit huge amounts of sand on top of the oceanic crust. Taking an even closer look, we can tell by the grains present in this rock that this particular greywacke is composed of lots of different materials and minerals, exactly what we would expect. And that will be about it. With these rocks at Deception Pass, we've covered just about the entire Fidalgo ophiolite sequence from bottom to top. So with that, we have one more stop at a piece of the last terrain to be accreted to the Pacific Northwest, Silesia. From near sea level on Fidalgo Island, we're headed southwest and up in elevation to get a good outcrop of our final terrain. High up in the Olympic National Park along Hurricane Ridge Road, we find evidence of the last terrain to be accreted to the Pacific Northwest, a terrain named Silesia. Silesia began as a giant undersea volcanic plateau. One model proposed for its formation? Well, let's imagine a huge outpouring of basaltic lava at a mid-ocean ridge not far offshore, similar to modern Iceland, though without the lava actually breaching sea level. This undersea plateau was then transported towards the growing North American continent, where it jammed into the subduction zone and was tectonically forced upward and accreted. So how do we know that it might have been an undersea volcanic plateau? Well, first off, it's huge. Rocks correlated with Silesia stretch from here in the Olympic Mountains, north to Vancouver Island, and south to the southern parts of the Coast Range in Oregon. Second, it's what the rocks tell us. This outcrop is full of pillow basalts. Again, these are the structures that form when basalts are erupted in a submarine environment. Each one of these lobes in this outcrop is an individual pillow. The Silesia terrain is full of pillow basalts and other mafic igneous rocks mixed with marine sediments. Another great example is Mary's Peak in the Oregon Coast Range. It's actually the highest point in the Coast Ranges outside of the Olympic Mountains, and that's because Mary's Peak is held up by a gabbro sill that's part of Silesia. Now, as we mentioned before, Silesia was the final terrain to be accreted to the Pacific Northwest, and full docking of this terrain happened around 50 million years ago in the Paleogene. And now, Silesia is part of the greater accretionary wedge that is forming above the modern Cascadia subduction zone. So, to recap, quite a busy trip. Our first field trip ended with rocks that formed along the passive margin of Laurentia. But around 200 million years ago, the tectonic settings shifted dramatically with the breakup of Pangaea, and the proto-Pacific Northwest became an active margin. Along with the initiation of subduction, we get the accretion of numerous exotic terranes. The first major accretionary event took place in the Jurassic, roughly from 200 to about 170 million years ago. These terranes include parts of the intermontane superterrane in the Okanogan Highlands and the accretion of terranes in the Blue Mountains and Klamath Mountains of Oregon. The second major group of terranes accreted during the Cretaceous, between 150 and 100 million years ago. These terranes include parts of the North Cascades and much of the San Juan Islands. And most recently, Silesia accreted in the early Cenozoic, around 50 million years ago. And with the accretion of this final terrane, the Pacific Northwest had grown to approximately its modern size. Now, if you thought this history of terrane accretion was crazy and wild, just wait until you see what happens during the rest of the Cenozoic. To say the least, lavas, megafloods, and megafloods of lava. We'll get to that and much more on our next field trips. See you then.